This is Team ABV, and my name is Anuj Patnaik. For the overview of our project, we are planning to reduce traffic congestion. We are doing this by reducing the amount of time a car spends at a traffic light. We can't simulate this for a whole city, so for our project, we scale it down to 9 intersections. But this idea can easily be scaled up to a city, which obviously has more than 9 intersections. We place cars at random starting points, and we choose an ending point for those cars. We have 2 lanes on each side. We also included all directions: right turn, left turn, forward, and merge. We find a set of directions that will get the car to the ending point as quickly as possible, and we move the car accordingly. We also test all possible light combinations to find the optimal light combination for the direction that we found. And we have the
Hello, my name is Vishwa Prakash, and I'll be going over some specifics about the road grid and how a car moves along the road. So first, signals at every intersection are paired so that there's smooth traffic flow. So for example, these 2 lanes would always be green while the others are red. These 2 lanes would always be green while the others are red, and then it would move on to these 2 and these 2. Cars don't move across an intersection unless their designated light is green. And each car has a predefined starting point and an ending point that are not at the same intersection. So a car cannot start here and end here because those 2 lanes come out from the same intersection. And finally, some roads are more congested than others because more cars would enter from certain roads than at other roads. Now to explain the legal actions. So in this grid, green dots represent cars and each letter G represents a green light. In the simulation, some of these would be R to represent red lights. Now, first, a car can move forward. It can move forward 1 space when it's not at an intersection, or it can move forward at an intersection across it if its designated light is green and the car is on the right lane of traffic. For turning, a car can move from the left lane of traffic to the corresponding left lane of traffic if its designated light is green. And the same thing applies for a right turn. If the car is on the right lane, it moves from the right lane to the right lane. Finally, merging, which is a simple diagonal shift forward. This action can simply occur if the car is not at an intersection, so it cannot merge onto the intersection like this. And finally, an overarching rule is that all of these actions can only occur if there is no car at the spot the car has to reach. So in this case, car number 3, which is turning left, cannot make this turn because there is a car already sitting here. And car number 6 cannot make this merge right because there is a car in the position that it has to go.
So when we move cars, we have a certain priority on how they move. The reason for having cars with certain priority is so that cars moving in the same direction don't collide. The reason we have to check this is because we are updating the cars discretely and not continuously. Here's the order for the cars. Cars closest to the exit point for their cardinal direction are evaluated first. If there are 2 cars next to each other, the car that needs to merge merges first. So it'll merge first, then the car behind it can move forward. Also, we make sure that cars turn left or right only when they have to. For example, if a car needs to turn left or right during their route, it will only do so at the last possible point. Other than that, the car will continue to move forward. The same logic applies to merge. It only merges when it has to, and other than that, it will continue to move forward. And last but not least, the order in which we determine the cardinal directions are north, south, east, and west. In the next part of the video, we'll show you the pseudocode for our simulation.
Hello, my name is Bhargava. Let's quickly go over the pseudocode for our simulation. So the first thing we should do is we create our road grid and the signal matrix, which we went over. And then we spawn, and in our case, 100 cars at the start. They are spawned at the edge of the grid at predetermined starting points. And they are created over the course of the simulation. Also, the ending points of each car is stored. We update the cars in their priority order. And as previously mentioned, the cars will take the shortest possible path to get to their end destination. We keep track of how many iterations a car spends with no movement for each intersection, and that will come out later. And then we update the signals based on the intersection times. That's part of our optimization process. And then once the car reaches the end of the grid, it is destroyed and its wait time is logged. Okay. So now to the signal optimization process. So starting with some basic definitions, a state matrix holds the cycle times for each signal. So L11 refers to the time allotted for the forward movement on intersection 1. And all those are essentially weights stored in a weight matrix. Using these weights, we run a simulation. This simulation will return 2 things. 1, the time lost at each intersection. So that's what I1 to IN squared represents. And then a total loss, which is the sum square root of I sub I. The reason we're using square root is so that we penalize a lot of cars waiting for a long time over an individual car waiting for a long time. So now a move is defined by increasing one entry in L by either -1 or 1 and leaving the other entries the same. So A will represent a set of moves, and each move AI can be either, so for example, increasing this one by 1 and leaving the rest from 0. Okay, so now on each epoch, we iterate through all the matrices and we find this we use this to determine which AI was the most effective based on the starting L and then our set of moves. Basically what it does is it finds out which AI reduced the cycle time by the most, or reduced the loss by the most. Okay, now to the procedure. So like as mentioned, we determine L and A at the start. These are randomly determined. On each epoch, we first find what is L or what is the loss given L of A. We determine the most valuable moves that we made. And then we essentially update A to keep only the top N most valuable moves. And then we keep doing this until we get down to our most valuable move. And all these moves are conglomerated, right? So we never undo a move. Once a move has been made, it stays. So for example, here on epoch 0, we had 7 randomly assigned moves, which we did on a random matrix L. Our loss there was 230. After that, we selected the top 6 random moves. We kept the top 1 and then generated another 5 random moves. Got there, kept the best, generated another 4, got there, and then so on and so forth until we get to our
Now, because we focused on making a scalable version of this program, there's a lot of room for improvement. There are 2 kind of categories here. The first is accounting for human behavior. This includes incorporating yellow lights, making cars travel at different speeds, and incorporating smart cars to ensure an almost constant flow of traffic. These account for how humans erratically change their behavior on roads when they just need to get somewhere on time, just blitzing past yellow lights or just switching to another lane just to move 1 inch forward. Another improvement would be a more complicated road system to ensure more rules to be followed. So more intersections, more lanes of traffic, merging from other roads, different types of road rules, things like that. Now, finally, and most importantly, why is this program crucial? Well, the purpose of the program is to process large amounts of data obtained from Uber drivers over a certain time span, say a year. After that time span, we optimize the routes of Uber cars with that data to minimize the waiting times for passengers. That time could accumulate from waiting for their ride or waiting at traffic lights during the ride. So the program isn't really for the everyday person to use. It's not really like your GPS. Rather, it is used by Uber HQ to update the Uber app for drivers so that the route calculated takes into account all the up-to-date information on the traffic patterns and, more importantly, the signal patterns and the delay caused by waiting at those signals. So this process, upon continued refinement over time, will ultimately cause total ride time, waiting time, and riding time to be optimized.
Thanks for watching our video.